Right, welcome back. What we are going to do, I've uploaded that recording by the way, so it will be there. It's doing still YouTube checking stuff. Okay, so it'll be there soon. Right, so what are we going to do? So you need to open up this PowerPoint, and this tar file I suggest you bring over to your Linux. If you want to play along, bring over to your Linux environment. All right. So let's have a look and see this. Here we go. Okay. So what is all this about, right? So what I'm going to do is I'm going to give you a little very simple C programs. All right. You don't need to be C expert. All right. You don't need to know anything about C. You just need to know how to compile a C program and run it. And the exercises we will do in the labs are, anybody can do them if they understand mutexes and semaphores, which hopefully you will. And what's mutex and a semaphore, I'll tell you in a few minutes, all right? The whole point about this is multiple threads accessing a counter that's in that shared data area that we talked about, all right? So remember, the thread controls the execution, the process controls the resources. So the process controls the global variable, in our case, what we will see is a counter, right? And the two threads are trying to write to the counter at the same time. And the whole point is, just like we had with the script, whereby we wanted to control the access to a shared resource, we want to use certain methods, which are called mutexes and semaphores, to control access to this global shared counter in this case, right? Okay, so that's what we're going to do, just to show you this in operation. So what you need to do is, as I say, you need to bring that file across. So I have one I made earlier. So if I go to my directory and I go to mutex, I've brought across that tar file. Okay, so that's what it looks like when you bring it across. So if I go tar, we all know how to run tar stuff now. I'll see A1 tar xcf mutex.tar. I get these files. So feel free to play along or just watch whatever you want, and you can come back and play yourself when the video, if you watch the video. Okay, so we have all these files. So the first thing we need to do is I just need to show you how to compile and run a C file. Okay, so you guys at this stage have done have you done Java, whereby you have to compile any Java stuff and then run it on the command line, or is it just all Python you've done and a bit of JavaScript? So have you done any Java where you use Java C? I think it's all Python and JavaScript, isn't it? Oh, you did a little bit. Okay, some of you probably did. Not on the command. Okay. I know some of you have done C with Jimmy and all that sort of jazz. Anyway, as I don't worry, anybody can do this, right? The most important point is with a C file, you have to compile it and then you run it, all right? So there's two steps, and it's simple as that's how you compile it and that's how you run it. So if you take this files that I gave, right, there's a hello.c and hello.2. So if you literally follow the instructions and type gcc, which is the compiler, -o just means create an executable output file called hello. You can call that anything you want, right? And hello.c, right? So I'm going to try that here. gcc -o hello.c. Okay? And that's it. If you don't get any errors, it compiles. It's right. So I now have an executable called hello. And if you run it, like the instructions say, you get hello world, right? That's the most simple C program, right? There it is there. Okay, literally a main, print, and that's it. Yeah, I can change that to be, let's say, you can use nano or whatever you want to use. I'll just change that to Pierce, right? Just to show you how easy it is. And then the more point is you have to recompile it. If I just run hello again, I'm going to get the old one. I have to recompile it because I changed it. And then run it and I get hello Pierce. Okay, That's your first C program, the most simple C program, right? Now, if we go on, the other thing I want you to make sure you understand is in a program, just like any other script or any other language, you can call other functions, right? So here's the same program, but it's doing a very simple change. There's the main. It calls a function called print string, which in turn just does the print there, right? So that's hello. That's hello2. So if we go and have a peep at that, and we go hello2, then I go hello2. There we go. Right? Simple. Now, I haven't done any threads yet, right? This is just the basics of get you running with a C program first. So hopefully everybody should be able to do that. If they don't do it now, they can do it when they look back into the video. And by the way, we will do this stuff in the lab anyway, so don't lose heart if you don't quite get it this week. You'll get it next week if you pay attention. Right, so now let's try something a little bit different. We're going to use a program which has some threads, and I'll show you the program in a minute. But the first one is called my T1, my first thread program. All right, so let's go and compile it. And you'll notice that it says you need to add in something extra, which is GCC minus pthread. And all that means is you need to tell it to use the pthread library because you're using threads. If you try compile it without that option, you will get something like this. Okay, and basically all that's giving you is an error saying, hey Wally, you're trying to use the pthread library, but you haven't told me. You're trying to use something and I can't figure out what this is, so you need to tell me what library to use. Okay, so all you have to do is tell it to use minus pthread, and then it should compile, and it does. Right, now let's have a peek at the file. Okay. Again, it's very, very simple. All right, there's a slightly more complicated main here, right? So again, I don't want you to understand C. All right, what it's doing is it is creating a thread, which is a thread is just a lump of code, right? Some function you have decided you want to thread. In this case, it is the function called count, which is the one up here. And all count is doing is adding, see it there, literally for 10 million times, it is adding 1 to a variable called sum, which is a counter, right? So that is going to add 10 million to that. Okay, and if we have a look here, we see I create a thread, I print the sum, and then I create a second thread, same thread, and I do it again, and then I print the sum. So before I run it, when I print that, what answer am I going to get? Anyone? Is there anybody out there that wants to talk to anybody here? My daughter sneezing. Come on, be brave. I'm not going to bite. What's the answer going to be? So it's going to count from 0. It's going to, for 10 million times, it's going to add 1 to the total that starts at 0. That's what the thread's going to do, 10 million. But then it ran the thread twice. So you're close, Taiwu, but what's the answer? It ran the thread twice. Go on, if I have to drag it out of you, 20 million. Brilliant, right? We all agree it should be 20 million. So let's try it. So I did compile it. So I'm going to run it now. My T1. There we go. 20 million. Yeah? We're all cool. We agree. Hard luck when tests. It's 20 million. Believe me. Okay. So that's a very, very simple program. Now, and it's a multi-threaded program. Or is it? Is that a multi-threaded program? In the true sense of the word multi-threaded, which is threads running in parallel, is that a multi-threaded program? Why do you say no, James? Or Calvin, why do you say no? Exactly. What I've done is I have run a thread, let it finish, and then run another thread. Okay. So the thread creates a join, starts it off, and then obviously run to finish. Okay. So I've sort of cheated there. They're not actually running at the same time. So let's have a look at my T2. Okay. Similar program, but this time I create the two and then I join the two immediately. So what's actually going to happen here? Excuse me. Hiccups. What's going to happen here is it's going to create a thread called count. It's going to run it, and in parallel, immediately, it's going to create a second thread called count. It's going to run that. So the two of these are now going to run in parallel, updating this counter. So it's a bit like, remember we did the script and they were both writing to the file. In this case, they're both going to write to that counter. The two threads. It's going to blast away, adding one. Yeah. So let's compile that one and see what happens. So I'm going to say play along if you want. And then I'm going to run it. Oh dear, I didn't get 20 million. I got nowhere near 20 million, right? I didn't even get 11 million. Okay? Why in the world did I not get 20 million? I don't expect you to know the answer, right? But here's the problem. The two of them are basically milling along at top speed, right? Trying to run that line of code. Yeah, they're flying around that little loop 10 million times, trying to add one to some. Well, why wouldn't that work? Like, that's one line of code. Surely that should work. And the reason why it doesn't work is that isn't actually one line of code. That is approximately 3 lines of code in assembler code. Remember your computer architecture again? That's a great course. So much you could have learned from that course. When you go sum plus equal 1, that's not what's called an atomic instruction, which is, it's not just one instruction. It is 3 instructions. What happens is the variable sum, the contents of that is loaded into a register. 1 is added to the register, and then the register is written back to the variable called sum. So there are 3 commands that actually happen. And guess what? When the 2 threads try execute those 3 at the same time, you can get corruption. And I'll show you exactly the corruption you get in the next deck. But I wanted to show you what the problem was. Okay, so in order to fix the problem, we need to make that line there. So let's just cheat here for a minute. So that line, I'm going to put a comment in here. This is not actually one instruction. It is 3. Okay? We need to make those 3 instructions not interruptible. Yeah? We need to make sure that you cannot interrupt those 3 instructions, because if you make it so that the 2 threads can go at that line at the exact same time, you are going to get corruption. And that's why threads are great, but you have to be really, really careful about how you control how they access global data, right? In this case, variable. In our case with the script, it was a file. Remember the file? Remember we had to make the bit that wrote out to the file, we had to make it so that the 2 threads or the 2 scripts could not get at that at the same time. Remember we did that? So this is the exact same idea. So let's keep going with the PowerPoint for a minute. Okay. We did that. We did this and it didn't work, right? Why? Because they're trying to add 1 to the sum variable, and it requires the CPU to load the variable from memory, increment it, and restore it. So it's actually 3 things. And as we know, this group of operations, the word that you're looking for is atomic, right? And it's a really, really important word. It means it's indivisible. It comes from the whole idea that, you shouldn't split an atom and things like that, right? So we need a mutex. What the hell is a mutex, right? So let me see. Will I actually show you this just yet. No, I won't show you this just yet. What I'm going to do now is we're going to go back and we're going to have a look. Now that I've explained to you I've shown you what the problem is. I'm not going to show you the fix yet. We're going to go have a look at the theory. All right. So let's have a look at the theory. So if you look up we're going to look at this one now. See this one here? Load this one up. Okay, so we have a thing called race conditions and critical sections. Wow, this is going to be good. A critical section is a fragment of code that can be executed by multiple software threads, which can in turn cause a resource, blah blah, to be corrupted due to concurrent execution of multiple threads. So concurrent thread execution can cause corruption. Well, we have just seen that, haven't we? We have just seen multiple threads try execute some critical section of code, and we ended up with corruption. Right? We didn't get our 20 million. We lost a load of increments. Right? So we have literally just seen that. Right? So the critical section, you need to understand what these definitions are. The critical section is the fragment of code that can be executed by the multiple software threads. So, what's the critical section in that file? What do you reckon is the critical section? Okay, so sum isn't the critical section, sum is the variable. The critical section, the minimal critical section is that line, okay? Some people would say, you could say that that's the critical section, but the minimal critical, the line that causes the problem is that line right there, okay? Now, it could be multiple lines, but in this case, it's one line, which in turn is actually 3 lines of assembler behind that, okay? Assembler is that load stuff, ink stuff, store stuff that you did in first year, right? Every line of a high-level language converts into multiple lines of assembly code, all right? You need to understand that, whether it's Java, whether it's Python, whatever. It all boils down to that assembly crap that you did in first year, all right? So anyway, that's the critical section. We term the corruption problem that can happen, and I stress can happen, I'll explain that in a minute, a race condition. It doesn't mean it will happen, it means it can happen, or it's possible. So what I mean by that is, if you were to take this code and you were to run it on a very slow computer, like Google, in fairness, this stuff is quite quick. If you run this on a very slow computer and you made that number smaller, you mightn't see the problem. You still have a crap piece of code, but you mightn't see the problem. The issue is, in real life, what happens is people write shite code, this stuff is in it, and when they test it, it doesn't happen. And when it goes out in the field, once every 3 months, it happens and the thing crashes, costs them a fortune to fix, and they don't know what the problem is, right? I've seen it happen. So you need to be aware how important it is to be aware of stuff. And if you ever see something happen when you're testing it and then it doesn't happen again, don't ignore it, because it means there's an intermittent problem and it's going to happen in real life and it's going to come back and bite you in the ass, right? So if you ever see an issue, chase it down. Don't assume, oh, I was seeing things. You weren't seeing things. There was an actual issue. All right. So that's the critical section. We term the actual corruption problem is the race condition. In other words, 2 threads are racing through the code at the same time. They're racing through the 3 lines of code at the same time. And depending on how those 3 lines of code line up, which I'll show you in a minute, you can have this issue whereby you lose increments, right? The term comes from having 2 threads, blah, blah, blah. Running the threads isn't the problem. The problem is resource access, right? Remember, the process controls the resource. The resource is, it's this global variable. The resource is not inside the thread. If the resource was inside the thread, you wouldn't have a problem. The problem is you have this global variable controlled by the process and multiple threads are trying to access it. So the running of the threads isn't the problem. The way they're accessing the resources is the problem. The resource could be a variable, in our case it's a variable, could be an array, could be another object, could be a database, could be anything, right? We saw it with files. Here's a question for you. Is the write or the read a problem? If it was just reading the variable all the time, would there be a problem? Calvin says no. Is read ever a problem between threads? Think about it. Anybody? So, Calvin's right. You can read to your heart's content. There's not a problem. Writing is the problem. Hard luck, Miller. So problems only arise when you write. Reading is safe, okay? The resource value doesn't change. It's just reading a counter. You can read to your heart's content, all right? So here's what I'm going to do now is show you what's going wrong with the fact that, here's my mouse, that is actually 3 lines, not 1 line, okay? I'm going to show you what actually happens. So let's pretend we have simple code to add a value to a variable. In our case, we're adding 1. In this little case here, we're going to do it with, we have a variable that starts off life as 0, and we're going to have 2 threads. One adds 2 to it, and one adds 3 to it, all right? So the pseudo code is read the current variable from memory into register, add the value, store the register, okay? So that's, in our mind, this is what you see, right? So we start at 0. The first fellow is going to add 2. So that's like sum plus equals 2, right? And the second fellow goes add 3. It's like sum plus equals 3. And in our mind, we see that it happens like this. So in other words, the current var into memory into the register, that would be 0. We would add 2 to the register. So the register now contains 2. We would store the register to memory. So the register, the 2 is written back out to the var in memory. Cool. That was the first line. Then the second one, read the current var from memory into register. So the 2 would come in to the register. We would add 3 to it. We would get 5 in the register. And then we would store 5 to the memory. So hopefully everybody can see that's how we go from 0 to 5. We added 2. We added 3. We got 5. But if you have the 2 threads and they're running in parallel and you don't have any protection to guarantee that these 3 lines are not interruptible, you get things like this. So the first thread gets to run his 2 lines. Then he gets scheduled off, right? His quantum is up. The next guy gets in and he gets all 3, and then the other guy gets rescheduled. So who's the genius? Tell me, what's the final value of the variable now if this happens? Is it 5, is it 3, or is it 2? Kelvin says 2. Anybody else? I usually get a random number generator at this stage. Here we go. Colin says 3. Anybody want to go with 5? Okay, let's work through it. I read the current value into the register. 0, we all agree, is in the register. I add 2 to the register. The register now contains 2. We agree? So register is 2 at this point. Read the current var from memory into the register. What's going to be into the register now? Zero. Great. Add 3. 3 is the register. Store the register out to the memory. What's in the memory now? Yeah, Luke is right. 3 is now. And then we go store the register to the memory. What does this register contain? It contains 2, because remember, on a thread, you have your own copy of the registers for when you're scheduled in and out. So 2, when this guy got rescheduled, 2 is in the register, and we write that out to the memory, and we get 2. So the answer is 2. What happens if I switch the last 2 lines? Anybody? 3. Let's have a look. Okay, Yes. If you work through it, you'll find the same thing. So be careful. When it's the red register, remember it has its own copy of the register. So therefore, what's in that one is not what was in that one. Okay, let's have a look. Here's another one. What's the answer? 5, 3, or 2? Anybody? Who says 2? Anybody else? Let's work through it. Current fire into the register, 0. Current fire into the register, also 0. Add 3, store memory. Memory now contains 3, we all agree. Add 2 to the register. What register? Well, sadly, the green one, which was 0. So we get 2. We store that out. So the answer is 2. Okay? Hopefully you get it. But you can see now how this gets screwed up. Okay. So the 2 threads, blah, blah, blah. That's okay. Fine. No big deal. So the code in our edition contains a critical section. And we now have seen multiple threads execute this critical section, race conditions occur. Fine. How do you fix it? In concurrent programming, which we know means threads in parallel, something is atomic if it appears. What does atomic mean? Indivisible or uninterruptible. We want to make these 3 lines uninterruptible, right? So that we end up with that effect, all right? That's what we're looking for. So we need to make sure that, oh, sorry. So that one, apologies on that. My mouse is, sorry, my mouse is gone missing here. Hello, mouse. There we go. Sorry. Okay, that's interesting. Prevent me from that. Okay. There we go. Sorry. Okay, we're back. Still missing mouse. There we go. We want to make those atomic, or in our case, we want to make that line atomic, right? That's how we're going to fix it, so that you can't be interrupted. So let's go back and see what it says. So that's what that means, right? So atomicity preferred is a guarantee of isolation from interrupts, signals, concurrent processes, and threads. Once we start something, it will finish before it gets interrupted. Interrupted means we will not get scheduled off, right? That's what it means. Nothing else is going to get scheduled. We are guaranteed to finish our 3 lines of code before someone else gets in. That's all it means. So to prevent race conditions, we must make sure that the CS critical section is executed as an atomic instruction. That's basically okay. I've already said that. Making a critical section atomic solves the problem. But remember that thread 2 is waiting while thread 1 is finishing. So throughput is an issue. Okay? So say a critical section was updating 2 variables. Should we protect a critical section with 1 lock or 2? So what that means is, say we had 2 different sums here. Should we just protect it 1 or 2? We'll get on to that in a minute. I'll tell you the answer in a minute. For smaller critical sections, making the whole critical section atomic may work. For larger critical sections, it may be beneficial to break the critical section into smaller ones to allow multiple threads to execute a smaller. Again, I'll show you examples of that in a minute, and it will make it more understandable. All right. Essentially, what it means is don't make something atomic for longer than it needs to be. All right, because if you do, you're preventing other people accessing the code, right? That's essentially what it means, but we'll show you. And that's what I'll explain that as we go through it. So how do you prevent race conditions? In Java, have you come across anything in Python or Java called synchronized? Have you ever heard of that? Synchronized is the word that these high-level language use to mean atomic, all right? What it means is it's not interruptible. If you have a synchronized method, it means that method, when that method starts, no other thread can also run that method. That's what it means until it finishes. Okay? In the OSs aren't written in Java, so we have to use different mechanisms, right? So I'm going to show you. I'm going to show you how to fix it. Right? Let's go back over here, and let's go back to our little PowerPoint. Okay. So we're going to use a thing called a mutex, right? So let's have a peep. How are we doing for time? A few minutes left. Oops, reconnect. We're going to fix this problem that we had, right? Remember what our problem was? We had my t2.c, okay? And we had this, and if we ran it, we got this effect. Yeah, we never got our 20 million, okay? So we're going to use a thing called a mutex. So if you look at it, my t3.c, oops, if you spell it right. Oh, sorry, it's my, what is it? It's not my t3. It's my M1. My apologies, my M1, my mutex one, right? We now have a couple of extra functions here. See it here? First of all, that's the same. We have our counter. We now have a thing called a mutex, right? For all I want you to do at the moment is think it's like a lock, right? And basically, if I use that, I can, if I say, give me the lock, then no one else can get in, right? That's all I want you to understand. So I've written a little function called getLock, which basically gives me, and then I have release lock, which is release the mutex, right? So the mutex is like a padlock. So in other words, if I get it, no one else can get in until I say release it, right? So I've got these two functions here, and I've still got my counter thing here. There's my critical section, right? And this is the exact same as it always was, the two threads. So let's compile that one and see how we get on. Minus p thread. Oops. Minus O my M1. My M1. Let's see. Okay. And I compile it. Let's run it. Oh dear. It's still a lot of crap. Right? See it? Why didn't it work? Who's awake? Why didn't it work? Anybody? I have my functions called get the lock release. Now, why didn't it work? I didn't call them. Well done, right? So for those of you who are awake, that's the critical section. I needed to protect that critical section. Yeah. So I need to put my get lock and my release lock. So if you look at my M2.c, you will see I've now done that. So before my critical section, I have said, give me a lock. And what that means is the first thread will get in at some stage, it will get the lock, and it will be able to do this line without the second thread getting in. The first thread will then release the lock, and the second guy will get in. But what it means is that line there, which we know is 3 instructions, those 3 will never be interrupted. Okay, so let's try this one. So this would be 2. Now we try it, and hopefully, yoo-hoo! This is 2 million, by the way. It's just I just reduced it. See, okay, it works. We fixed it. Deadly. So we fixed it, and that's all that's basically saying, right? Now, however, we put the fix around. See it here? We put it there and there. If you look at my M3.c, you'll see I've put it in a slightly different place. See it there? Will that work? Anybody? Anybody reckon that'll work? Do you reckon that'll work? Oh, will we try it? So let's compile. Milan reckons no. The bad news is Milan is it is yes. Okay, let's try it. it works. So why does it work? Because you've basically said, give me a lock, count to 1,000,000, and then release the lock. So it's going to work. However, I'm going to ask you a question. In this particular program, so there's 2 threads. There's the thread code. There's the lock. How many times in this particular one, my M3, is the lock requested and released? How many times? Twice is the answer, because there's 2 threads, right? So the first one comes in, grabs the lock, it counts to 1,000,000, releases it, then the second guy gets in, right? Whereas in this one, how many times is the lock asked for and released? Exactly, 2,000,000 times, right? Which is better? Calvin says the twice one is better. Everybody seems to say, why? Because, well, it's quicker, right? It's going to be a lot quicker. And if I do this, oops, sorry. So if I do this, right? So how many is there? 11. Okay. So they both have 11, agreed? I need to do that. Okay, so do. That's the MyT2 one. And okay, so we all agree that the MyT3 one is way quicker. So for some people, they would say, well, that's much better. But what have I actually done? Sorry, my M3. What have I actually done by doing that? What's the effect of the multi? I had a multi-threaded program that was in parallel, counting up to 2,000,000, right? By doing that change, what have I done? By putting the locks at the start of the for loop and at the end. What have I done to the effect of the 2 threads? Are they now running still in parallel? No. I've actually made them sequential, right? Which you may want to do, but that won't always, well, one run first. Whoever gets in first, Tywee, right? It doesn't matter. Like in this case, I would be surprised if this one didn't get in first, because it was called slightly before the other one. But the issue is, if there was something in here you wanted to be done in parallel, then this is a bad solution. So when I said which is the best solution, I should have said which is the fastest solution, definitely M3. But which is the best solution? It depends on what you're trying to do. If you want to do stuff in parallel, you have to go for the first solution, okay? The M2 one. So hopefully you understand that there's a difference, and that's what I was talking about when I was talking about, you know, where do you put the critical sections, and it depends on what you need it for. There's one more, which was M4. Why does it hang? So let's compile M4, and then I'll let you go. M4. You run it, and sadly, my M4 hangs. And seeing as you're all awake now, why does M4 hang? Anyone? Why does M4 hang? I would expect one of the programmers in the room The return is stuck. Okay, the return isn't stuck. The return returned. The issue is, as Paul says, the release never gets called because it's after the return, right? So what actually happens is the first guy comes in, he gets the lock, he counts to 1,000,000, he returns, he's finished. The second guy comes in and he calls get lock, but it has never been released. So it basically sits there. If I put a printf in, the current value would be 1,000,000. Okay. The first guy got to do his business. The second guy never got in because he's going to sit there forever. And that's another problem with threading. If you get it wrong, you can hang your code. All right. So you need to be really, really careful. And that's basically okay. Semaphores we will do in the lab, and you get to play with those. All right. So let's just go back to where I was. Give me that one. Okay. That was it. Right. So what we have done is we did a lot. We did a lot. Fair play to you. So we've done this, this, and this. Okay. What we'll do at the start of the lab next week is we'll do the second part, which talks about some of the other, it just goes back over a little bit and talks about some of the other solutions you can do in OS land, right? We're going to concentrate on semaphores. What's a semaphore? Well, I'll explain it to you in the lab. And then I'll actually, in the lab, we'll start to do some of the exercises and you'll get to learn about where to put these things to start and stop stuff. And there's some really nice stuff I think you can do. And this, I guarantee you, this is in your CA2, all right, in some shape or form. And I'll be honest with you, CA1 is easier than CA2, so I hope you did well in CA1 because CA2 is a little bit more tricky usually. Okay, so you need same rules. If you do the labs, you should be fine. If you don't do the labs, then you're going to have a major problem. All right. Any questions on that before I let you go? Hopefully you enjoyed it. Hopefully you got something out of it. Hopefully your brain isn't fried. Okay, I shall let you go and I will see you next Monday for the labs on this particular subject. All right, so be good, take care.